Hello, everybody. My name is Jason Go. I'm in the studio with Santosh George and Dylan Poole, and the three of us are part-time MBA candidates at the Robert H. Smith School of Business at the University of Maryland. Go Terps. Through FedTech and the U.S. Federal Lab System, we've partnered with Dr. Ben Taylor of SPAWAR Pacific to bring Dr. Taylor's patented process to market.
So what does a Hyperloop, a bullet train, a MRI, and more recently, advanced industrial motors have in common? Superconductors. Superconductors work at very low temperatures. There are primarily two types of superconductors. The low temperature superconductors work at minus 400 degree Fahrenheit, and there is a significant cost involved with cooling. The high temperature superconductor, though, they work at minus 200 degree Fahrenheit. But now, since liquid nitrogen can be used to cool the high temperature superconductors, the cooling costs are much lesser. But then there is a problem with the YBCO. It's brittle. It's not possible to machine YBCO. Think of it like a ceramic plate. The invention we are demonstrating today is a manufacturing process that makes it possible to machine YBCO. Now, what does that mean? That means now you have a superconductor that has a lower cost for cooling and is also machinable. Now, isn't that the best of both worlds? We started by looking at where is YBCO a good fit today, but cannot be used because it is not machinable. Our initial conversations with Ben Taylor led us to research superconductivity in MRIs, and that's where we started our journey.
We started with a simple hypothesis or value proposition. With our technology, an MRI device manufacturer could begin miniaturizing these superconducting magnets in MRI machines and ultimately make the entire machine portable. During our interviews, we actually learned that our customer's manufacturing process called for low temperature superconductors, whereas our technology was only applicable to YBCO, a high temperature superconductor. So we had to pivot and move up the value chain until we identified the manufacturers of these small magnetic sensors that could increase the speed and precision of an MRI scan. These sensors were called squid sensors, and our technology was definitely applicable to squids. We confirmed this time. However, squids aren't used in the traditional MRI device we see today. See, in today's devices, the strength of that large magnetic coil offsets the need for a strong or stronger squid sensor. What we had heard about in the market were experimental low-field MRIs, which, instead of a magnetic coil, use Earth's relatively low magnetic field and rely heavily on a powerful squid sensor. Customer demand for this pretty nascent technology were less than desirable, so we ultimately decided to move on and further up our supply network.
We moved up the value chain to the thin film YBCO manufacturers. Here we discovered squid sensors are a small market and not a focus for any of the firms we talked to. We did discover that one major focus market for these companies was utility power transmission cables. One of their core products are high-temperature superconductive tapes, which are multi-layered flat cables with thin film YBCO inside. These high-temperature superconductive tapes can carry 3 to 5 times the current of traditional copper wires without the 7 to 10% resistance loss wasted with these copper cables. We rigorously tested our hypothesis that our process could improve the high-temperature superconductive tapes for utility power transmission, but determined that the mechanical properties of the tapes are sufficient for today's market demands and that the greatest limitations today are manufacturing consistency and cost, neither of which our process improves, thus nullifying our hypothesis. During our conversations with the thin film manufacturers, we received multiple inquiries on whether or not our process could be used to create nanochannels or nanowires to make high-temperature superconductive tapes into multiple independent conductors. Once we confirmed with Ben Taylor that our process could be applied in this way, we followed up with the tape manufacturers, who further explained the potential value of this nanochannel wire in high-frequency applications. Applications like those found in aircraft engines and wind turbine generators, where high-filament wires are used today to reduce heat. If nanochannel tapes can be proven to mimic properties of high-filament wire in high-frequency applications, these would help eliminate the design constraints here and prove to be highly valuable.
We covered a lot in our 12 weeks. As you can see, we spent the first couple of weeks cold calling every big name in healthcare and big pharma. Week 3, we started getting uncomfortable, moving to markets outside the Fortune 100. We looked at quantum computing, cryogenics, even terahertz imaging for security detection. In week 6, when we had our first market correction, we actually reopened a dead lead in supercomputing. And finally, the program's last 14 days is where the potential of a go-to-market strategy really started taking shape.
We believe that the most feasible go-to-market plan for our technology would be to partner with and license the process to one of the high-temperature superconductive tape manufacturers we have identified.
Now on to the next steps. So we recommend a 3-phase approach to monetization. The first would be a proof of concept where the nanochannel tapes are created using the manufacturing process. Once we have that, then use them in a high-frequency motor and prove that this results in a much higher efficiency, high-frequency motor. This is where we recommend a partnership with GE would help. Once we have these steps done, then it's time to think of monetization. And we recommend that licensing the technology to HTS tape manufacturers is the right way to go.